Hello everybody. So, welcome to my third lecture, where we are continuing our topic, that is on the structure and geometry of the carbenes. So, today I will continue again on that particular topic. What we have learned, that carbenes are in general triplet and singlet, right. Okay. So, once it is like this, now the next questions will come into our mind, that is which type of carbenes that will be triplet and which kind of carbenes that will be like a singlet. So, if we see, in general triplet carbenes whose bond angles in general higher, we have discussed previously why its bond angles are higher. Bond angle in general 130 to 150 degree, whereas singlet carbene that is its bond angle are in general 100 to 110 degree. Okay. We have discussed its reason, that why singlet carbene is less and why triplet carbene is more. However, here now we will see the examples. In general the triplet carbenes, that is like this. So, CH2 carbenes, then CHPH or CHR are here alkyl groups or diphenyl carbenes, and the singlet carbenes are dichloro or it is CHCl or dimethoxy carbene. Okay. So, just examples, few examples. Now, next question is that why these are triplet carbenes and why they are singlet carbenes. Okay. So, even though all these carbenes they can be stated as triplet or singlet, but why some of these carbenes are actually preferring to be triplet and some of these carbenes are preferring to be singlet. Okay. So, now if we see something is triplet carbene means what? So, triplet carbene means triplet state is actually lower in energy than the singlet state. So, it means triplet state is lower in energy than the singlet state. What does it mean? Again, it means that if the repulsion exists between the two electrons in a single orbital is higher than the energy that gained by bringing the p orbital electron down to into the sp2 orbital. So, basically if some carbenes is singlet means there will be 2 electrons in same orbital. So, there will be some repulsions. Now, if that energy is higher, okay, if that particular repulsion energy is higher, then we are getting or we are gaining the energy by bringing down the p orbitals electron into the sp2 orbitals, then basically that will be triplet. Okay. That means the repulsion energy that is higher. Once it is like this, that means always these carbene wanted to be triplet, okay, because in that case it will be lower in energy. Is it clear? Okay. So, we can write here that repulsion exists between two electrons in a single orbital is actually greater than energy gained by bringing the p orbital electron down into the sp2 orbital. If we make it very simple, that two electrons when it is in particular orbital, let us say as for example sp2 orbitals. So, they will have some repulsions. Now, that will have some repulsive energies. Now, once something will be in a triplet state. So, if we wanted to bring down that particular electron from p orbital to the sp2 orbital, then it will gain some energy. Now, depending upon which one is higher and which one is lower, now these carbenes will determine whether they will be in a triplet or singlet state. Okay. Now, if this gaining energy from bringing down from p orbital to sp2 orbital, this gaining energy is higher than the repulsive energy, then what it will be? Please tell. If the repulsions exist between the two electrons in a single orbital, if that is the higher, then obviously what it will be? Triplet. But if the opposite happens, that means the energy gaining, it is when you are bringing the electron from p orbital to sp2 orbital, that energy gaining is higher than the repulsive energy, then obviously that will be singlet. Okay. So, now we will see that what will happen when we will give, let us say, dialkyl carbenes. Okay. That means for sigma electron donating substituents, what will happen? For sigma electron donating substituents. Okay. So, what will happen for these things? As per example, dialkyl carbene. Okay. So, for sigma electron donating substituents, that if that presents in the carbene, then how it will behave. Once this sigma electron donating substituents is there, what will it do? It will induce inductively. So, what it will do? It will inductively induces to smaller non-bonding sp2 orbital and p orbital gap, which favors the triplet state. Okay. If we see, if you remember in my last class I showed that how this can be shown in a electronic configurations, let us say like this. So, for this bonding we have given the sigma, then this is like sp2, then p and then the sigma star. Now, we filled up these electrons like this for p orbital for this triplet. Now, what sigma electron donating substituents will do? No, that is inductively induces to smaller non-bonding sp2 orbital p orbital gap. Okay. That means, to basically due to presence of this sigma electron donating substituents in the carbenes, that means like this, let us say like this. So, if these two are sigma electron donating substituents as per example alkyl groups, they will inductively induce to decrease the gap between the non-bonding sp2 orbital and p orbital. So, they will try to decrease this, and once this energy will decrease, then obviously this carbene wanted to stay as a triplet state, because the energy difference between this sp2 and p is now lower. So, it will remain as triplet state. So, what will happen? Triplet state favors. Okay. So, if you see in our previous slide, there we have shown that as per example like this. Here if you see, I have shown that triplet carbenes all are like this, that parent carbenes molecule CH2 carbene, CHPH, or the alkyl group having alkyl group carbenes, those are actually stays as a triplet carbene. Okay. Next, we will see that carbenes having electron rich substituents with lone pairs. Okay. So, previously what we have learned? We have learned carbenes having the substituents with the electron donating sigma electron donating substituents. Now, what we will learn? We will learn carbenes having electron rich substituents with lone pairs. Okay. As per example, you see this dichlorocarbene. Okay. We can write this one like this. Now, X are having lone pair. This X could be OR, SR, NR2, Beer, Cl, etc. So, now we have all those things. If this is the case, then this carbene, these can be stabilized by the adjacent lone pair. Okay. Okay. So, this carbene can be stabilized by adjacent lone pair. Fine. How it can stabilize this one? If we see its orbital overlap, okay. Now this is the X that is having this lone pair, we can think like this, and this is the sp2 and p. Okay. Now, once this orbital will overlap, they will generate lower energetic new orbitals. Okay. How it is? Now, we will see. So, this is like this. Now, this lone pair of this X, it can give to the vacant p orbital. Okay. So, now we will see that how these things can be filled up. Sorry, this is we have done, this one is here. Okay. So, now the electrons, if we think, so like this and like this, and this is the field n orbital. Okay. This is the adjacent lone pair. Now, and this is the partially filled orbitals of triplet carbene. This is partially filled orbital of triplet carbene. Fine. And this is the sp2 non bonding, this is the p. So, p orbital, and then finally, you will get more lower energetic orbital, where it can stays as a singlet. Okay. So, what does it mean that these adjacent lone pairs in this type of carbenes are actually stabilizing these carbenes as a singlet one? Clear? So, the overall view of this particular type of carbenes is that when there is sigma electron donating substituents, then that is actually lowering the gap between the sp2 and p. So, overall the energy difference is decreasing between them, and as a whole it remains as a triplet, but the carbenes which are having electron rich substituents with lone pairs, they are staying as a singlet because of the filled n orbital of this adjacent lone pair that can stabilize this type of carbenes, and overall these type of carbenes are becoming like a singlet. Okay. So, now depending upon the adjacent substituents, how many type of carbenes can be? As we already mentioned that this stability of this carbene, stability of these carbenes are actually depending on their substituents. or rather I should say not stability, rather the nature of this stability and nature, rather I will say stability and nature of these carbenes depending on the substituents, right, the associated substituents with this. Now, depending upon that, depending upon the adjacent substituents, depending upon the adjacent substituents, there are three types of carbenes. One is called nucleophilic, another one is ambiphilic, okay, and another one is electrophilic. Okay. So, there are three different types of carbenes: nucleophilic, ambiphilic and electrophilic. Obviously, it depends on their adjacent substituents, fine. As per example, nucleophilic is this, I am giving one examples. This is example. For ambiphilic, this is COMeF carbene, and for electrophilic it will be dichlorocarbene, fine. Now, if we see this particular type of carbenes, we have discussed this one, this type of electrophilic carbenes. Now, nucleophilic carbenes like these dimethoxy carbenes, they are devoid of electrophilicity towards alkenes. Why? Because of the electron donation by the methoxy group. How? So, if we see okay. Now, that can give. So, in general it can be like this. Fine, okay. Or it can be from this side. So, sorry, okay. So, this type of carbenes, that is why devoid of electrophilicity, devoid of electrophilicity toward alkenes, okay, because of electron donation by the methoxy group. So, there are these three type of alkenes are there, like nucleophilic, ambiphilic and electrophilic, and in general these dimethoxy carbenes, they are devoid of electrophilicity toward alkenes due to the donations of the electron by the methoxy group. Clear? Our next topic is that we will start, that is called persistent carbene. What is this persistent carbene? In general, we found that most of these carbenes, they are actually very short lived. Carbenes are in general are short life. Okay. Now, there are certain carbenes which are stable. Certain types of carbenes, they are stable. Okay. These are called the persistent carbene. Okay. And obviously, if some carbenes are stable and can be detected by various spectroscopic method, then obviously these confirm the existence of carbene. Okay. So, even though it is short lived, but due to presence of certain type of stable carbenes, we can confirm that carbenes are forming. As per example, one of the very important example in this regard is this. This is called Arduino carbene. Okay. And in absence of oxygen and moisture, it exists as stable and colorless crystal, whereas its melting point is around 240 to 241 degree centigrade and bond angle is 102 degree of this carbenic carbon. In general, in 13 CNMR spectra, it has been found that this carbenic carbon that will give at peaks at 211 ppm, which reflects that this carbenic carbon is highly electron deficient. And this particular carbene has been developed by Arduino and co-workers, developed by Arduino and co-workers, and that is why these are called Arduino carbene, and this has been developed in 1991. Okay. In the next class, we will learn why this type of carbenes are stable, what kind of factors made this stable, and with that we will learn few more persistent carbene. Okay? Thank you.